All right, good afternoon, everyone. So we've been talking about feature selection, and this slide kind of summarizes it well. We learned in the last unit that if we use too many features, the problem is our variance increases and then our mean squared error increases. We also know that if we use too few features, then our variance is low, but our bias increases. And so what we really would like to do is to use as few features as possible, but in particular leave out the ones that are not helpful and include only the features that are most helpful. And that is the problem of feature selection. So we want to figure out the best subset of our D total features. So, so we learned about the optimal strategy, which is exhaustive search. So in that case, you would test every possible subset of features. There's a total of 2 to the power D of them. For every one of those subsets, you could fit the least squares model. You could use k-fold cross-validation to evaluate those fits. And the problem with this is that testing that many subsets might just be impossible. It might be too large computation. So last time we learned about stepwise selection, where you might start with no features, then you find the single best feature. You keep that, you find the single next best feature to add to it, and so on. So that has D squared complexity, but it's not optimal because maybe when you chose that first feature, that second feature, you would have later wished you didn't choose it, but you can never get rid of it once you chose it. So those are greedy schemes. And we also talked about correlation-based methods, which try to exploit correlations between the features and the target when you look at them one at a time. And we will spend most of the rest of the unit on regularization-based methods like lasso. So let's start talking about that. Okay, so we know that when we do our least squares linear regression, we find the betas that are the minimizers of the residual sum of squares. So that's the difference between our training targets and our predictions of those training targets. And our goal right now is to somehow modify this optimization problem to also perform feature selection at the same time that we're training our coefficients. So the main idea is we're going to add something to our optimization objective that penalizes the use of each feature. So realize that if we chose beta j equals 0 for some j, that means we will not be using feature xj in our model, right? I'm just going to multiply it by 0. It's the same as ignoring it. So essentially, we need to add something to this RSS. We're going to call it function phi of b that somehow increases as we increase our betas. So as you move beta away from 0, this imposes a penalty. And so it basically says, you better be sure about using that feature because your RSS may go down, but it needs to go down a lot before we're going to make it worthwhile to use it. So that's the main intuition behind adding that penalty. And we're going to call the sum of these two things j, and we're just going to then minimize j. So we have another optimization problem, but now we're adding this additional term that, that tells us to be careful when we turn on features, when we set the betas non-zero. Does that idea kind of make sense? Any questions about it? Yeah.
Maybe just flip the notification arm and then beta.
Yeah. So if you look at just the minimum value of RSS, that would be like the lowest possible RSS you could get. When you look at the argmin, it's the minimizer. It's the beta that gives you the lowest RSS. Does that make sense? So if we didn't have the arg here, it would be like RSS min. But then once we have the arg there, it's actually the beta that minimizes the RSS. So it's like the difference between the minima and the minimizer.
Okay.
All right. So is this idea of penalizing our training objective making sense? Any questions on that? Okay, so we're going to talk about two possibly different ways to penalize it, and we'll see that these have very different behaviors. So, and they're both mathematically pretty simple. The first one is our penalty function is going to be some scalar alpha, which we will choose, times the sum of the squares of our beta coefficients. So this is what we call L2 regularization because this is known as the squared L2 norm. So this is actually something we saw back in Unit 2 when we talked about the Euclidean norm. We'll talk about this a little bit more in a couple pages. Another option, instead of putting a square there, we can just leave off the square, and then we're penalizing the sum of the absolute values of the betas. So to understand a bit about how these differ, let's just look at the case of a single beta j. So when we look at the quadratic case, we have this quadratic this parabola. But when we look at this case without the square, we have this function. So the big difference is how they behave close to the origin and how they behave far from the origin. So when you look close to the origin, you see that the L1, the red line, the red curve, is actually a bigger penalty, right? But when you look far from the origin, you see that actually the quadratic is a bigger penalty. So that's sort of the difference, is that quadratic really cares about not making betas very big, but it allows them to be non-zero. It doesn't really care very much if you perturb them from 0 a bit. Whereas the L1 doesn't care as much about betas getting large, but it really does care about you perturbing them from 0. Okay, so that's going to have very different effects on how the regularization behaves. So they do both penalize the beta. Both of them have this alpha coefficient, which is something we have to adjust. Eventually, we will tune this alpha using something like cross-validation, but we're going to talk a lot about this today because there's different ways to do it. And one thing to note is that we are not including j equals 0 in the sum. So we are not applying our penalty to the intercept term beta 0. So the idea is that beta 0, we definitely want to fit that no matter what. That is not multiplying any features, so it's not really involved in feature selection. So we're just going to penalize the beta j's starting at j equals 1, which are the ones that multiply the different features. Yes?
Do we really need to take the absolute value of beta in the first one?
No, we don't. When we deal with real numbers, we can replace this with just a parenthesis. So that's a good point. Okay, any other questions? All right. So now is a good time to talk about something called standardization. We talked about this a little bit last time, but when you look at these two penalties, you notice that all the different beta j's are treated the same, uniformly, right? There's the kind of penalty applied to beta 1 is the same as applied to beta 2 and so on. So the thing is that if your features xj have very different sizes, like if some features are tiny and some features are gigantic, then the corresponding beta j's will have maybe the opposite sizes, right? Because like if one xj is tiny, I need a big beta j to make it have any effect. And if one xj is gigantic, then I'm going to probably need to make beta j small, otherwise it will swamp out everything else. So the problem is that if you have xj's of very different scales, then the beta j's won't be calibrated, and then these penalties will sort of unfairly penalize the large betas, which correspond to the small features, right? So we don't want that to happen. So to prevent that from happening, we want to pre-process our data by normalizing it, making sure that all the xj's have roughly the same size on average over the training samples. So, so the most common thing people do is for every fixed j, they just force the mean squared value of xij. So this is right. This is looking at all the different training samples I for a fixed j. They want to set that to 1. So another way to think about that is you have your sample mean squared, xj bar squared, and you add your sample variance, and you want to have that equal 1 for all the different features j. Okay, so that is essentially what we could call normalization, and that would get rid of this problem that we're talking about here. But there's something we can do in addition that makes our life easy. If we also remove the mean of both y and all of the features, so just compute the sample mean and subtract it, then we saw back in unit 2, that will force our intercept coefficient, beta 0, equal to the value 0. And that way we don't have to fit it, right? We just know it's always 0. So, and this is a very easy thing to do, is to take out the sample mean. So this is a pretty common thing that people do as part of data preprocessing. So if you put these two things together, the normalization and the mean removal, that is called standardizing your data, both removing the mean and dividing by the standard deviation here. So here's like what we do for the features. So if I'm talking about all my samples xij for a fixed j, I'm going to subtract the sample mean, and then for the result, I'm going to divide by the sample standard deviation. And I'm going to just call that, the same thing. So I'm just going to apply this normalization and give it the same name. That's what this arrow means. And I'm going to do this also for the targets. I'm going to subtract the target sample mean, divide by the result by the sample standard deviation, and those will be my new targets. And then I'll fit my data with these standardized values. Okay. Any questions on the procedure? Yes.
So we want to have sample variance of 1.
It's just an arbitrary number. They could all have sample variance of 10. The point is that we want these values here to be uniform over the j's.
Yeah, so I guess my question is, how would we get, is the square root of the sample variance is the standard deviation, correct?
Yeah.
So
Yeah.
we're dividing, does it matter if we divide by the variance or the standard deviation? Which one gives sample variance of 1?
Since we're dealing with, so we definitely want to divide by the standard deviation. So this is like you could call it a linear quantity, whereas this would be a squared quantity. So you don't want to divide a linear quantity by a squared quantity. They're like apples and oranges. Does that kind of make sense? Yeah. So standard deviation is also like linear scale. So that's the way you'd want to normalize it. And it's not too hard to see that if you do this, and if you do this procedure, I think there may be a homework problem. If you do this procedure and then you check to see what is the sample mean and standard deviation of the new standardized values, you can prove that yes, they're mean 0, standard deviation 1, or variance 1. Okay, was there another question? Okay, everybody good with this procedure? All right, so this is implemented in sklearn. I mean, it's easy to do by hand, but if you want to use sklearn method, it's just done using what's called standard scalar. So first you instantiate this scalar, and once it's instantiated, then you fit it to your data. So now you give it, so this would be, in this lab, x0 is are the raw unstandardized features. And so this is a function, fit transform, that does two things. The fit part of it figures out these two statistics that it needs, and the transform part applies those statistics in this operation. There's also a fit method alone, which would just compute these quantities and store them internally in the scalar. That's useful if you want to apply those quantities later to another variable. So here you can see we're normalizing the features and storing them as XTR, X training. And here we're going to do the same thing to the targets. Now there's a little snag here that this method wants you to give it a matrix and not a vector. So to get around that, you have to convert your vector of targets, one-dimensional tensor, to 2 dimensions, and then apply this, and then we can shape it back to a vector. So that's what this reshape stuff is doing, going from a vector to a matrix and back. And then, so this is how we get the X and Y training, how we standardize. Yes?
So what would that matrix look like? Is it like a diagonal matrix or?
It's a good question. So if you're used to MATLAB, everything in MATLAB is a matrix. So when you make a vector, it's actually a matrix. Let's say it's a column vector, then it's a matrix of size, n by 1. But Python and NumPy is different. NumPy, if you have a vector, it's just a one-dimensional quantity. There's no notion of it being a column or a row, because when you think about it that way, you're actually saying it's a two-dimensional quantity, which allows you to say which way it's, right? So the one-dimensional quantity, it's neither column nor row. It's just a list, essentially. So NumPy is different that way. So when you take this this vector and you make it a matrix, you're basically making a matrix which is going to have one row and however many columns. That's all it's doing. And now it's officially something of dimension 2, and this function can process it correctly. And then we're going to convert it back by reshaping that thing, which was like a row vector, back to just a list of numbers, one-dimensional quantity. Okay. Is there another question somewhere? Oh, that's the same question? Okay, yeah. That's a NumPy peculiarity that's different from MATLAB. All right. Any other questions? Okay. So there's one other important thing is that this procedure is for how we standardize our training data. When you want to standardize your test data, because once you standardize your training data and you train a model on that standardized data, it is expecting that all the data it sees is standardized. And so if you didn't do anything to your test data, it would work terribly. Okay, so you have to standardize your test data. Now the question is, how exactly do you do that? Do you use the sample mean and sample standard deviation computed on the test data to standardize the test data? Or do you use the sample mean and standard deviation computed on the training data to standardize the test data? Anybody know? The training numbers, yeah, it's written here, so it's kind of obvious. But this is something that a lot of students get wrong, and when you get it wrong, things work, but your performance is a little bit worse than it could be in most cases. So you especially see this like on the project in the end. You just can't get performance that's quite as good as your classmates. And it might be because when standardizing the test data, you're actually using the test data statistics and not the training data statistics. So that's one important thing to know, is that you're always computing these numbers based on the training data. Another way to think about this is imagine that you had just one sample of test data. In that case, it's impossible to even compute the standard deviation, right, for your test data? So, yes.
Couldn't you just standardize all of it and split it? Standardize all the data and split it into a test train?
So that would be illegal, because that would be that would mean you're using, so usually we have like what we're calling test data is something we do not want to use at all during the training process. If we do, it kind of corrupts the training process and it leads to overfitting. So we want to hold that test data separate and not use it at all unless we're using it for validation. So if I used it in this way, it would actually become part of my model. And then it would be, it's like you're using that test data as training for this scaling part of your model. We wouldn't want to do
like on validation data.
Oh, the validation data.
I mean, like, is that validation data is what you just split off from the original set?
Yeah, so you always compute these numbers from the training data, and then those numbers are what you use for test and validation to standardize it. Okay, you don't want to compute numbers from those data sets.
So standardization and normalization are about restricting a data between -1 and 1, right?
No.
0 and 1, anything.
No, it's not the same as that. So it is about making the sample mean 0 and the sample variance 1. So for example, let's just assume it's Gaussian. If we have Gaussian data and you make the sample mean 0 and sample variance 1, and you plotted a histogram, you would definitely see values sometimes that are above 1 and below -1. Right? So there is a different form of standardization which bounds it within an interval. Sometimes people use that. In some applications that might make more sense. But that's not what I'm suggesting here. Yeah, sometimes like if you're working on a project and you're really trying to, get that last bit of performance, you can try different ways of standardizing and see how they affect you. And sometimes one for a particular data set might work a little bit better. But this is like the standard approach. This is sort of the standard go-to first thing you do.
Feature scaling has no effect on the efficiency of our model. I mean, it could definitely increase the computer efficiency, but then the final RSS would always remain the same. So how can we define what kind of feature scaling actually affects our model?
So I'm just presenting, I'm giving you justification for doing it this way. So if you scaled so that you're between 0 and 1 or 1 and -1, you would not get a sample mean of 0. You would not get this property to hold. You could have different, depending on the distributions, you could have different variances and so on. So it is an option, but I'm just suggesting it's not the first option to consider.
That's okay, man. I understood that. But my question is that you just said that for a final project we could try different types of normalization standardizations. But I read somewhere that feature scaling has no effect on the model per se. Right? The
Oh.
RSS value will not change. It will only
So in homework 2, you proved that for linear regression, least squares linear regression, feature scaling has no effect. But that is a very special case. In almost all the other models, it does have an effect. And so now that we're talking about regularization, it definitely has an effect. Okay, great. Okay, any other questions on this stuff? Okay, good. So now let's get back to talking about these two options for regularization. So one of them we said is we take our RSS and we add onto it our L2 regularization. And another way to write this, we saw this before, we can write the RSS as the norm. We're basically just stacking these yi's into a column vector and stacking these into a column vector, but then noticing that that y hat can be written this way. So this is just rewriting this as a norm. Now, one thing to note is in this definition of beta, I am leaving out the beta 0 term, right? And this is because we know that beta 0 will be 0. So we're just leaving it out of the model completely. That means that I don't have my A matrix with the column of 1s. I don't need that column of 1s anymore because I'm not even including this beta 0 in this vector. So now I just have the feature matrix X. So it's slightly different from what we did before. Anyway, this is how we can write this term using a norm. And then we can write this as alpha times the norm of our beta vector. And this norm, whenever you don't see anything in the lower right corner, you can that means that it's the usual norm for that space you're working in. Since we're working with real numbers, arrays of real numbers, this usual norm is the 2 norm, L2 norm, or Euclidean norm. So, but if you wanted to be, really explicit, you could write little 2's down there. The reason why it matters is because over here, this is the L1 norm, and so we write a little 1 in that lower right corner. Okay, so here we have the squared L2 norm. Here we have just the unsquared L1 norm. Getting back to how we can interpret these norms, imagine that I have, this is, let's say in 2 dimensions, this is my beta vector. If I want to measure the distance, the Euclidean distance, or the Euclidean length of that vector, I start from the origin, and I look at the distance, or the length of the line from that vector to the origin. Right, so this is going to be the d equals 2 case so that we can draw it. This is like beta 1, beta 2. Right? That's the length. That's the length of as the crow flies from here to here. That's the length. Now the L1 norm is also a distance metric, but it measures it in a different way. It measures it. I'll do it in red. It measures it as this distance plus this distance. So sometimes people make an analogy with a taxi cab in Manhattan. If the taxi cab wants to pick someone up around the other side of the corner, they cannot drive through the block. They have to drive down the street, make a turn, and then drive up the street. And this is another way of defining distance. So it's equally valid. It's just different than the Euclidean norm. So I'll put a little, this is like L2, this is like L1. All right, so is that difference between the norms pretty clear? Okay.
So which one would be which in this case? Which one is like, I guess, more punishing for larger?
So yeah, so what we saw is that when you look at each term in the L1 norm, it's this. So it's more punishing for small numbers, but less punishing for large numbers than the L2 norm. Yeah.
Saying I had a negative beta, would the regularization change the sign?
Yeah. So we're always looking at the absolute here, and then this also cancels the sign. So it's symmetric with respect to the origin. Right? Positives and negatives are treated the same way.
But would the net beta change to a positive if it was used to meet the y?
We'll see some examples that tends not to happen. What tends to happen is that things get shrunk towards the origin with these two types of regularization. L1 tends to make it go all the way to the origin, and L1 just pushes it a little bit towards the origin. But we'll see some pictures coming up.
So if you have a lot of data, would you want to use the L2 regularization?
We'll talk about the motivations in just a moment. Okay, so yeah, so let's first talk about L2. So this, when I don't know where this name came from, but when you take RSS and you add L2, it's called ridge regression. When you take RSS and you add L1, it's called lasso. Stands for I think it's the least absolute something and shrinkage operator. Scaling and shrinkage operator. Just weird names, but everyone calls this lasso and ridge. Okay, so let's talk about ridge first. So this is the ridge cost we saw on the previous page, written as a sum, written as norms. And one nice thing about this cost is everything is quadratic, and as you've seen until now, quadratics are very nice to work with analytically. So you can derive, without very much trouble, you can do the minimization of this on paper, and you will find that the minimizing parameters take this form. So this is exactly the same as what you saw with least squares, except now there's this plus alpha I inside the inverse. That's the only difference. And alpha is a tunable parameter, so you can choose how strong you make this term here. So one thing you can note is that even if this matrix is not invertible, when you add this, it is always going to be invertible. So this is something we talked about. I think in the last unit we said if you don't have enough data, what can happen is this matrix is not invertible, and now you can see that's not an issue with this. We also saw it with one-hot coding. If you one-hot code in a redundant way, you'll get this to be non-invertible. Now with this, the invertibility is restored. You can do this inverse. Okay, but the real reason that people tend to use ridge regression is that it helps when you have correlated features. That's the real use for it. So this is what happens essentially if you do least squares regression, so you don't have this regularization, and some of your features are very correlated to each other. And what happens when you look at the eigenvalues of this matrix, some of them are going to be small, and some of them are going to be large. It's the small ones that really matter because when you invert that matrix, those small ones can become very large. And what that means is that you can have very large prediction coefficients beta. And for the training, that's okay because those are actually what gives you the smallest training error. But then when you use them for predicting in the test case, these very large values can amplify small noises, and you can basically see overfitting. So this is something you don't want to happen. You don't want this matrix to have very small eigenvalues because when you invert them, they become very large and cause problems. So by including this, you make the eigenvalues no smaller than alpha. And then that prevents them from being very small, and it prevents these guys from being very large, and it helps with all this. So basically, at the end of the day, it reduces overfitting, and especially when you have highly correlated features. Okay? So.
How are eigenvalues coming into the picture, like Pareto?
Why are we talking about them? Yeah, I don't want to go too deep in them because let me just say, for those of you who know a little bit about eigenvalues, maybe what I just said is useful, makes some sense. For those of you who don't, we're going to talk a lot more about them in a later unit, but I don't want to derail us right now. I'm just trying to explain a little bit what can happen in practice, and essentially you're going to see some large values here with correlated data, and that's why. So, yeah. If it doesn't make sense, it's not a big deal. The main thing to know is that when you use this, when you penalize according to ridge, you discourage the beta from getting too large and you reduce overfitting. Okay. Any questions on ridge? All right. So let's look at a plot of what happens. This is a plot as you increase alpha. So as we move alpha to the right, that means we have higher and higher penalty here. So we have a larger and larger effect of that. When alpha is 0, you're going to have just plain least squares regression. So back here, when alpha is a very small number, let's say it's close to 0, the values you get, so these are the coefficient values beta. This is whatever the least squares estimate would be. As you increase alpha, you can see that all those values shrink towards the origin. And as alpha gets very large, this is 10 to the 4th, you can see that they're getting very close to the origin. So you have like this knob you can turn, alpha, and that knob pushes your betas close to the origin. So this is something you have to choose carefully. If you choose it too large, you're going to bias your coefficients a lot, and your mean square error will suffer tremendously. But if you use it too small, in some situations, you can have very high variance, a lot of overfitting, so you don't want it too small either. You want it just in between at the right value, and we figure out that value using cross-validation. So it's very similar to the model order selection, but instead of having a grid of integers d that we did before, you have like a grid of floating point numbers alpha, and you just do cross-validation for different alphas on your grid, and you find the one which gives you the smallest cross-validation error. So in the lab where this picture came from, that dotted line shows that is the value of alpha that gave the lowest error on the validation of the test set. Right. So that's, in general, how we do things is we use cross-validation to figure out how to tune these things. Okay. So is this, yes, question?
Just wanted to know what has happened with the brown line. It's solving those up.
Yeah. Yeah, actually, someone asked this before, can it go up? So I guess it can. It's interesting that the brown line actually went up and then down again. So that doesn't happen with most of the lines, but it happened with that one. It happened a little bit with the green one. It changed signs. So I guess it can happen. It's just, I don't have a good intuitive explanation for why that is. But I guess you could say, like, when all these features are present, then you want to their coefficients to be in a certain way. But then as you start to suppress some of them, then others become more important and they have a different balance.
So they're not like independent.
Yeah, in general, all the different features, they all have some common information about the target. So they're all correlated in some way.
But sorry if I missed this, but like what would a good alpha value be in this case?
So that would be where the dotted line is. So that was found using k-fold cross-validation. So in the lab, there's a part where there's like a grid of many different alphas. For every grid point, you do k-fold cross-validation, you get the test RSS, or mean squared error, and then you find which of those grid points gave the best solution, and that turned out to be this value of alpha here.
Does that have anything to do with like, I noticed that like at the dot, the dotted line, that's when the lines like just start to change their size, like they look pretty much constant before that.
Yeah, so once they get really small, you can expect that probably there's a lot of bias going on. So you probably don't want the values to be hugely different from this, but yeah, you want them to be a little bit different. So it's hard to explain it. It really depends exactly on the data. Can't really say much beyond that. Okay.
We've already come across one optimization problem before, like for calculating RSS. In this optimization problem, we sort of decided, try to see what is the difference between this modulus and also squared norm, right? Like the L2 norm and the L1 norm. Why didn't we do the same thing while doing RSS? Is there a reason? Why did we just directly go with the squared and not think about the modulus?
Oh, why didn't we use like
Why did we
one
do
norm?
that? Back
Yeah.
then we just thought
It's a
squared
good question. So the squares are nice in that you can derive everything in closed form. And there's another reason which we'll talk about towards the end of this unit when we talk about maximal likelihood. But the RSS is the most common in part because, not only because it's the easiest, but because it is optimal in a certain sense when the noise is Gaussian. When the measurement noise is Gaussian, then this is the way you want to construct your loss. When the measurement noise is non-Gaussian, so one example is if your data has a few outliers, just like a few values that are really far off, that would not be like a Gaussian type noise distribution. In that case, you want to use a different loss function, and L1 actually is a pretty popular case in that case. So if you have outliers, L1 is better than L2. So we'll understand more about that next lecture when we talk about maximum likelihood.
But could we assume that for the purpose of this whole course, you're only going with RSS being the squared value?
So RSS is defined as a squared value. So in other words, it's like the L2 norm of the measurement error. So you could use the L1 norm, but another problem that we'll just talk about is you can't derive it in closed form. You need to run an algorithm to solve it. So that's another thing that's not as convenient about it. Okay, so we can do the same sort of thinking about lasso. So in lasso, we have our RSS, we add our L1 norm, and like I just said, one significant thing is there's no closed form expression for the optimal coefficients, the ones that minimize this lasso cost. However, this is known as a convex optimization problem. We'll talk about that in Unit 6, but it turns out what that means is that you're guaranteed to be able to compute the solution, and there's a lot of software out there that can do it for you. For this particular problem, because it shows up a lot, people have developed very specific algorithms that are fast, and some of the well-known ones are FISTA or ADMM or GLMNet. And these algorithms are implemented in sklearn as part of the lasso method, so they've already been programmed. You don't have to program them. It definitely, when you run this, it definitely takes longer to solve this problem than it does to solve this problem. So that's something to know. And now the question is, those are some disadvantages. What are some advantages of using this L1 penalty? So it turns out that one of the advantages is that when you have this strength alpha within a certain range, it will drive a subset of your betas exactly to zero. And what that means is you're actually doing feature selection. You really are turning off those features entirely and leaving other ones on. So in that sense, lasso is useful for feature selection, whereas ridge is not useful for feature selection. Ridge is good for correlated features, but it's never turning off your features, whereas lasso really does turn them off, it sets them to 0. So it's useful for feature selection. Okay, and also, as we'll see on the next page, the number of features that get turned off is proportional to alpha. So as you make alpha stronger, more and more features get turned off. Once alpha is large enough, all your betas are 0. The best thing you can do to solve this is to set all beta 0. That's probably a not very useful solution, but it's what happens if you make your strength too high. Now there is an issue we have to be very careful about, is that the beta j that are non-zero get pushed towards 0, and as such, they get biased. Their values are a little bit smaller than what we would like. And so what we actually want to do is we want to sort of do things in a two-step way. We first use lasso to figure out which coefficients should be set to 0, and then we take the remaining coefficients and we fit least squares. We fit them with least squares. Least squares is unbiased, whereas lasso is biased. So we want to use lasso only to do feature selection. To find the actual values of beta we use for prediction, we use least squares. Does that make sense? What I just said, or can I explain it in a different way? Any questions? So again, ignore the betas that come out of lasso and just keep the indices. So the set of integers j such that beta j is non-zero. And then, keeping those features, just give those features to your least squares solver. Okay, so that's how we want to use lasso. We don't use lasso to get the betas. We use it to figure out which betas to set to 0 and which features to use for our least squares fit.
Is this technique more efficient than just performing using the ridge regression method?
So ridge regression has a different purpose. It does not perform feature selection. It never sets any of the betas to 0. So if our objective is to figure out, a subset of features to use and a subset to ignore, we can't use ridge. Ridge just pushes all the coefficients a little closer to 0, but it doesn't really set them exactly to 0. So if I really want to do feature selection, which is figure out the subset, I have to use lasso, or we had other techniques too, the forward selection, backward selection, so on. Okay, and lasso is actually computationally it's slower than ridge, unfortunately, but it's probably one of the best methods to do feature selection. That's why we're focusing on it. Also, it teaches us a lot of other useful concepts. So, okay, so here's a picture of lasso's coefficient path. So again, similar to before, we're increasing alpha along the horizontal axis, and we're plotting the trajectory of the coefficients that are fit by lasso. And you can see that when alpha is very small, it's essentially the same as doing least squares. As you increase alpha, the coefficient values start to go towards 0. At some point, one of them turns off, then another turns off, then another turns off, and so on. And like down at this point, you only have a single coefficient left that is non-zero. So in that sense, you can kind of work your way backwards, and you can say, according to lasso, the most important feature is this one, which is LCA vol. I think it's like the volume of the cancer in the prostate. And then the second most important one is that purple line. And the third most important one is that orange line. And so lasso kind of gives you a ranking of features. It's not necessarily the optimum one, but it's kind of its analysis of which features are most important, which are least important. Okay, so again, two things happen. The betas get turned off, but that's good. But the bad thing is that the value of the remaining beta gets pushed towards the origin. That's bad because that kind of bias will also hurt you. So let's say that you somehow figured out that this was the alpha that you wanted to use, and that told you that there's only one more coefficient left. You don't want to just take this value, 0.3, You actually want to go back and solve least squares with that one single feature and take the value that least squares gives you for beta. Clear? Okay, question?
We use L2 regularization to reduce the values of beta close to the origin, right?
So yeah, if we use ridge regression, then we're using L2 regularization. And if we use lasso, lasso's L1. So there are two different options. There is also something called the elastic net where you use both, but we're not really going to talk about that, but that's another option.
But what is the significance of reducing that to zero, reducing betas close to zero? Because when we take the inverse, the value will shoot. So what's the advantage of taking it close to zero?
So no, it's sort of the opposite. We're not inverting the betas. The betas are the result of the inverse, and those are getting closer to zero. So when the coefficients are very correlated, if you did not use any regularization, you could find some gigantic betas. And so we're using ridge regression to make those betas smaller so that they don't hurt us when we apply them to test data. Okay, so then just to kind of summarize what we've said, lasso is one method that tends to produce many exactly zero-valued coefficients, which is great for feature selection, but the downside is there's no closed-form solution. We have to solve it numerically, and it takes a little bit of effort. Ridge regression, where we use the L2 penalty, the nice thing is we can write the solution in closed form. It tends to produce small values of beta, but not zero-valued, so it is not useful for feature selection, but it does help with correlated features. These pictures, sometimes you see these are visualizations of, if you looked at the L1 cost alone and you plotted equal cost contours, it would look like this. And here we're plotting the RSS cost alone, and what we're really minimizing is the sum of those two costs. And it turns out that minimum tends to happen right where these, if you start both of these from small and you grow them until they first touch, that's where the minimum tends to occur. And so here you can see, because of this sort of diamond shape and these ellipsoidal shapes, the minimum tends to occur along one of the coordinate axes, which means that this coordinate, that beta j, is exactly zero at the minimum. On the other hand, when you do this with ridge regression, this is your L2 penalty, this is your RSS. Here, the minimum occurs here, and as you can see, it does not occur on a coordinate axis, and so it does not give one of the betas equal to zero. So geometrically, these pictures are kind of explaining why lasso turns off features and why ridge doesn't. But if they don't make complete sense, that's fine. It takes a bit of mental gymnastics to understand what's going on there. Okay, so that's sort of the summary of these methods. And let's talk a little bit about implementation, because this is important. So first thing to note is that sklearn has a lasso method, not surprisingly. So looks like this, linear model.lasso. So it's part of that linear model package. And warmstart is just a parameter that if you want to call lasso over and over again and you want it to use the last value it found during optimization to seed the next optimization, that's what a warmstart is. And so what we're doing here is we're doing a manual programming of cross-validation. So we have the two-loop approach we saw before. So there's an outer loop here, which is we're drawing, we have this k-fold object, and we're drawing out pairs of indices from our k-fold object, and we're using that to establish what our test and training folds of x and y are. And then we have an inner loop, which for the inner loop, we construct a grid of alphas. These are the different penalties for L1. And you generally want to construct them on a log-spaced grid, not a linear-spaced grid. So we have this logarithmic grid. We're using 100 values. And then in our inner loop here, you can see we've instantiated lasso up here. So now that it's instantiated, we can tell that lasso exactly what its alpha is. And then we can fit according to our training data. And then we can predict according to our test data, gives us our predictions. And now we can look at the RSS, this is normalized RSS, the difference between the test predictions and the true test values. And we're basically filling in the entries in a big matrix, where on one dimension we have all the different model hypotheses, so those 100 values of alpha, and along the other dimension we have our k folds. And once we have that matrix, we can average over the folds, and we can find finally the RSS bar as a function of alpha, and if we want to do something like one standard error rule, we can find this standard error as a function of alpha too. So this would be the manual approach to doing it. That's fine. Turns out that there's a much simpler approach which you can do in essentially one line called grid search CV. We'll see this in a couple slides. But it's nice to see the manual approach just to understand what it's doing. And then that's scikit-learn just programmed this and gave it a nice interface. So, so now we have to be a little careful in terms of the bias of lasso. So there's actually it's kind of an issue with what we're doing here, which will show up in a second. But let's imagine that we just proceed, and we've computed these RSS values based on the lasso coefficients for different hypotheses of alpha. So what you could do is you could say, well, I'm just going to choose the alpha that minimizes my RSS. That's what we learned to do in the last unit, right? Or you could be fancier and you could use the one standard error rule. In either case, once you know that alpha, what you can do is you can now say, I'm going to use all my data. I'm not going to split it into training and test folds. I'm going to use all that data, and I'm going to compute lasso coefficients based on the full data for the alpha that I chose. And if we did this, we do this in the demo, it turns out, if you look at the code, the coefficients, actually looks like there's one of them that's exactly 0, or almost exactly 0, and there's another one that's almost exactly 0. So it should say 6 of the 8 features are, oh, actually, no, I messed up. Sorry, I didn't read. The first one that's 0 is the intercept coefficient. Remember that we expect that to be 0 because of how we normalize the data. So really, there's just one coefficient that lasso turned off at this particular alpha that was minimizing RSS bar. So now that we know that, we said, okay, don't trust these other values. These are biased. So throw them away. The only thing to keep is the fact that let's not use LCP in our model. So let's delete that feature, take the other 7 features, and give them to least squares based linear regression. And then, so here's how we can do that. We look at so the lasso model contains the coefficients. To get them out, you do lasso.coef. Then you look at the absolute values, and you figure out where those absolute values are greater than 0. Those are the ones we're keeping. That's going to be stored as a subset of integers. It tells you the indices. And then I'm going to extract only that subset of features and give that to linear regression. But here's where I'm using this fancy command cross-val score, we learned this last unit, or last lecture. So in cross-val score, we've created a linear regression object. Here we're going to give it our training data. We give it our k-fold object, tell it how to score, and it's going to do the cross-validation, and it's going to tell us finally what the scores are, and basically, what is the cross-validation MSE achieved by this model. So it turned out, you can see what happens. If you use the biased lasso coefficients, the MSE is not great. If you use the unbiased least squares coefficient, the MSE has improved. So yes, this is helping us. Okay, so is everybody with me so far? Okay, now there's sort of a little bit of a oversight that I made here. That's why I'm calling this the naive method. I don't know does anyone see what the problem is? There's something I did that's not quite right. Something we did that's not quite right is we said that we are going to get rid of these biased lasso coefficients. We shouldn't trust them. But it turns out that this RSS bar, when we computed that was using the lasso coefficients. So this is not a good way to choose alpha, because this is the best alpha if you use the biased lasso coefficients, not the best alpha if you use the unbiased least squares coefficients. So we're going to abandon this. We're going to think more carefully. And I'm going to show you two different options for doing it the right way. Okay, so here's the issue that I just explained. The alpha on the previous page was selected to minimize the RSS of beta lasso. We don't actually use beta lasso for prediction. We only use it for feature selection. Okay, so what we really want to do is we want to tune alpha to minimize the RSS of the lasso selected least squares coefficients. Okay, so here's how we can do that using a for loop. So we have our loop over all the different alphas we're testing. For each one of those alphas, we store it. We store that alpha in lasso. We then fit the training data. Then we extract the coefficients, look for the non-zero ones, and then finally, this is the cross-val score we saw. We finally do least squares based on only the subset of features that lasso found. And then we can store that mean squared error. And here's a plot of those mean squared errors as a function of alpha. And you can see they evolve in like piecewise linear segments. This is because for all the alphas in this range, lasso gave us the same subset of coefficients. It didn't turn off any coefficients between here and here. So that means the subset is the same, which means the least squares coefficients will also be the same. So that's why we're getting exactly the same mean squared error. But at this point, all of a sudden, lasso turned off a coefficient. So now the least squared coefficients changed. And then here they changed again and again and so on. So anyway, as you can see here, the cross-validation mean squared error says you should use alphas in this range, which will all give you the same set of coefficients, which are going to be the ones that minimize the least squares coefficients RSS. Okay, so this is a better way to do it. And if you look at the result, this is actually an improvement over the previous page. And we have one more thing to talk about. Is everybody okay with this method? Okay. Now, you could say, well, there's something that's even a little bit strange and uncomfortable about this, is that when we did cross-val score, at that point we were splitting our data into training and validation folds, training and test folds. But when we did the lasso part, we were actually using the full training data, the full data which had both training and test. So you could say that's not really the best way of doing cross-validation because we're somehow mixing things together in this stage and then separating them in this stage. So there is a way to do things so-called properly. And for this, we have to use a slightly more advanced tool within scikit-learn, which are called pipelines. The idea of a pipeline is you can pipe together several operations as one. And so what the operations we're going to pipe together and think of it as one big operation is doing lasso, extracting the non-zero features, and then doing a least squares fit on the indices of those extracted features. So if we think about this whole thing as an estimator, we can feed that to this grid search CV, do everything in one line. And then it's going to, it's going to do all this stuff using k-fold cross-validation. So how we do that is we build this pipeline. So we tell it the different pieces of our pipeline. Here you can see we have linear model lasso. And then there's something called select for model, which figures out which coefficients lasso did not turn off. And then we take the output of that and we put it through linear model, linear regression. So this is our new estimator. We're just going to call it pipe. And here's grid search CV, which is doing everything in one line. It's applying this model pipe to, it's looking at the different alphas using this cross-validation object and the negative mean squared error score. And once you set that up, you just give it your data and you fit it, and then you can basically extract the results. So it's very efficient once you get this thing set up. And the plot looks a little different now because as you change alpha a little bit, just a tiny change in alpha will change what happens in the many different k folds of cross-validation. You'll get different numbers of features selected. And so you have a more interesting behavior here. This actually takes longer to compute than the other method, but some people would say this is a more principled way of doing it. And you can see there's a unique alpha which minimizes the cross-val mean squared error here. So we could go one step further, and we could even do like a one standard error rule, where we look at the target would be up here, and we look for the simplest model that gives performance on that target. In this case, larger alpha means simpler models, so that means you would actually select this if you're doing the one standard error rule. This would be the alpha you choose, and that may work better. Actually, the mean square error performance of this method for this particular demo is not quite as good as this method, and it may be because we didn't do one standard error rule. I can try that out sometime, but anyway, just to give you one bird's eye view of all these methods that we've talked about so far in the demo, this is the cross-validation you get. So exhaustive search gives you 0.388. If you do plain least squares, that's using all the features, it's the worst. Exhaustive is the best, and then everything else is in between. You can find what ridge is. You can see what lasso is with the bias coefficients. Lasso with the d-bias coefficients, where you just look at least squares. But in that case, we were selecting alpha in a suboptimal way. Then we have the for loop way of lasso and least squares, the pipeline way. And then these are the recursive feature evaluation, and also the mutual information versions. And so what's interesting is the lasso least squares with the for loop is almost as good as exhaustive. The recursive feature evaluation is tied with lasso. Those are the two best. And the mutual information is bad. It's as bad as least squares. So this is not going to be the case for all data sets, but this is what happened here. So the best methods in this case were this for loop, lasso, least squares, and the RFE-CV. And of course, the very best is exhaustive search. So, so with that, we're going to focus, change our focus next time. This is enough for today. Sorry, I went a little bit over. Ask me questions after class if you have any. See you guys on Friday.